Hello, everyone. Welcome to this IBHA webinar. I have the pleasure to call on stage Lowell Gustafson, member of the International Big History Association and former president. Hello, can you hear me?
Hi, Hi, how are you?
Okay, I'm fine, thanks. And I'll call Professor John Little, our presenter today. Hello, John, how are you?
Yeah, hi, Daniel.
Yeah. So John Little received a PhD in environmental engineering from the University of California, Berkeley. He's currently a professor in the Department of Civil and Environmental Engineering at the Virginia Tech in Blacksburg, Virginia. His early research focused on process dynamics in environmental systems, but now John has broadened his research to encompass the Anthropocene systems. John has been a visiting professor at the University of Sydney in Australia, the Swiss Federal Institute for Aquatic Science and Technology in Switzerland, and at Tsinghua University in China, among other institutions. So you're welcome, John. Thank you very much for accepting this invitation. And I'll leave the floor to you. First, I'll leave the floor to Lo to say some words, and after that, you can start your presentation. Thank you very much.
Well, first of all, I just want to thank John so much for giving this presentation to us. I mean, it fits in with the kinds of conversations that we've been having in big history for a long time. We've talked about, are we interdisciplinary, multidisciplinary, supradisciplinary? What are we trying to achieve? And I think John advances this conversation beautifully in his system of systems research that he's been working on for a long time, that now has been recognized with a grant from the National Science Foundation, and he is well underway with his project. So again, John, many thanks for taking the time out to do this for us.
Oh, thank you, Lowell and Daniel, for making this possible. It's really a great pleasure for me.
Okay. So, thank you, Lowell. So, John, we will leave the floor to you. Okay, I will project your presentation. Here it is.
Great.
So, see you at the end.
Great. Well, thanks again. So, this presentation has the title has several terms that I'll start by briefly explaining. So, of course, you all know what evolution is. And then this is the sort of systems engineering side of the presentation. And then convergence is basically what it means is sort of deep integration across disciplines. And it's something that the National Science Foundation is pushing now. So then, of course, I didn't just get to this place without any other support. I had tremendous support from many other colleagues, and these are some of the key papers that we've published. And in particular, this one down here sort of picks up the big history theme. And so then the overall presentation has two halves to it. The first half is the evolutionary story, and which maybe you understand better than me, in fact. And the second half is the systems engineering side of the presentation. And then I'll kind of end with some conclusions. But I'm going to start with this sort of introduction to how the Anthropocene evolved and how these societal challenges emerged. So this is, I'm sure, the part of the story that you all know better than me, but billions of humans have transformed our Earth systems into what we can think of as Anthropocene systems. And this process has accelerated recently. So here we are only 12,000 years ago, the beginning of the agricultural period. And here we are now. The population went from about 4 million then to 8 billion now. So no macroscopic species on Earth has ever seen such explosive growth. It's an amazing thing. So then this is the story that I know you know better than me, but if we look at all these evolutionary periods here, then in the early period here, we just had geological evolution. And then once life emerged, then genetic evolution became important. And then in more recent times, cultural evolution has become important, especially for humans. And we'll kind of pick up those threads as we go through. So now I'm just going to briefly, recap each of these 8 evolutionary periods, but I know that you know this story very well. So this is, from the Big Bang to the Earth forming, and we get these geophysical systems evolving, including, the ocean, the atmosphere, climate, and hydrology. And then life emerges. And so from then on, we get genetic evolution becoming important. And then only 650 million years ago, we get multicellular organisms. And so in particular, then cognitive systems start to evolve in animals with nervous systems. And that leads all the way through vertebrates to mammals and primates. So then only 6 million years ago, we get the early humans. And, we have these like hunter-gatherers on the plains of Africa. And so then it's important to remember that cooperation and competition, and this includes conflict, were increasingly facilitated by cultural evolution. And it's these cultural norms and institutions that sort of moderate human behavior, and increasingly they do so now. So then 12,000 years ago, this was like that point I showed you on the graph. So then agriculture leads to, villages with domestication of crops and animals. We get zoonotic diseases, war, and pro-social religion. And now a group level adaptation becomes important. So then 5,000 years ago, we get urbanization, with some towns and villages and towns becoming cities. So we get more complex urban societies emerging. And then 270 years ago, we get industrialization, get steam engines, fossil fuel, and these big systems start to be developed very rapidly. And then 70 years ago, we have the sort of computer revolution, which really speeded up technological evolution. And now we've got computational science and digitization and social media. And maybe the key point to remember, to note now, is that all these systems are becoming increasingly complex and interdependent. So of course, they always were interdependent. We had plate tectonics and global climate, but now they really are much more interdependent and interconnected than they ever have been. And another interesting point is that from the point of view of humans anyway, it could be that cultural evolution is outpacing genetic evolution. So all of that brings us to the current situation. And what we have now is this nested evolutionary ensemble of these primary Anthropocene systems. It's shown down here at the bottom. We've got these geophysical systems, which we started with, and then we added the biophysical systems to them. Those are like ecosystems. And then now we've got socio-cultural and socio-technical systems, which are primarily the human systems. And you can see here in the table the kind of various categories and the examples of those different systems, but I'll come back to them in a minute. So then the important thing also is to realize that this whole evolutionary story gave rise to these societal challenges of the Anthropocene. These are the ones that we're facing as a sort of civilization today. So if you run your eye down this list of societal challenges on the left, let me just briefly go through them just to sort of emphasize the point. So we've got decarbonization, we've got eutrophication from nitrogen and phosphorus, we've got clean water, we've got climate change, pandemics, infrastructure, food and agriculture, plastics in oceans, biodiversity, renewable energy, healthy living environments, and disasters. And so, all of these societal challenges emerged because of those evolutionary mechanisms that I just briefly alluded to. And all of them are complex and systemic, as is shown on the right here, with interactions and consequences that cascade across this globally connected system of Anthropocene systems. And, they are framed, these challenges are framed in different ways. So people often use sustainability or resilience or increasingly equity. So now the next part is I'm going to tell you a little bit more about this evolutionary system of systems convergence paradigm. So on the right here, I have that same list of Anthropocene systems that I went through before. And let's just think about one of those societal challenges. Let's think about food and agriculture and think to ourselves, well, which of these systems on the right here is involved in the production of food, from agriculture? So, okay, maybe not geological so much, but ocean for sure if we got fish, and then hydrological, atmospheric, climate, soil, ecological, land use, energy, okay, agricultural, obviously some mining, then transportation, infrastructure, other, infrastructure, industrial systems. Much of food is like manufactured in a way. And then, of course, all the socio-cultural systems, so cognitive, communication, education. So basically, all of these systems are involved in food and agriculture, which is just one of those societal challenges. So let's think about it in a little bit more detail. So here on the left-hand side, I'm showing sort of the real world down at the bottom, and then 10 sort of hypothetical systems. So then, as is shown in the middle here, each one of those 10 sort of hypothetical systems has many subsystems, the smaller pieces of the larger system. And so then the subsystems within that one individual system, they all interact. Okay, and so that interaction gives that one system its own internal dynamics. And then those individual systems interact with the other individual systems via some of those subsystems. So it's not like they all interact simultaneously, they just interact via some of the subsystems. So then, the vast majority of research that gets conducted now when addressing these societal challenges, what most people do, because it's sort of almost constrained by our kind of institutional environment, most people start with their own little piece of one of these systems. Like I may choose a lake, in the hydrologic system, and I say, okay, well, if I manage my lake a bit better and I put some solar system there to get more power, and I improve the water quality, then I'm going to make the world more sustainable. Well, nothing could be further from the truth, because that's just one little piece of the problem. So we can think of that as bottom-up incremental research, which is sort of what we all tend to do when we try and address these societal challenges. But now let's sort of step back and think if that's going to be effective. So let's just assume that one of those societal challenges has 10 systems, as shown on the left here, and that each one of those systems has 100 subsystems. So maybe in an urban environment, you could have like an energy system, and it could easily have 100 subsystems. So then that means if you've got 10 systems, each with 100 subsystems, that's 1,000 subsystems in total. And if they can all potentially interact, obviously they don't all interact, but they can all potentially interact, that means 1 million possible interactions. And if we take this bottom-up incremental approach, where we just start with one little subsystem and connect to a couple of other subsystems, it's going to take thousands of research projects. It's going to take decades of research. And at the end of all that, we still won't understand how the systems interact, because we haven't characterized the systems themselves. We've just been connecting little subsystems. And that's just for one of those societal challenges, food and agriculture. And there are many of them, maybe 15 or more, and they're all interdependent. So what we're doing is almost, it's almost futile in a way. So you can think of it like this, here we've got, our kind of our societal challenge with 10 systems, and actually they're all kind of interconnected, as is shown on the right here. And what we do is we kind of look at one of them at a time and focus on that one and just forget about all the others, because it's all just too complex. So then there's even another even bigger problem, because when we characterize these separate systems, like the hydrologic system or the energy system or the economic system, we have what is known as our own disciplinary ontology. We sort of represent what goes on in those systems in quite different ways from other disciplines. So we have to overcome those disciplinary ontologies. We've got to have a common language that brings everything together in a kind of a unified conceptual model. And to do that, we need a common computational framework and a common scientific language. But if we tackle these societal challenges one at a time, then having a separate framework and scientific language for each challenge is for sure counterproductive, because they're all interdependent. And these bottom-up approaches where we just connect a few pieces, they're just never going to get to where we need to be. So it's completely clear that we need coordination, sort of how to coordinate our efforts across all these systems. And then we also need to integrate what we do in a way that's much more, orchestrated than we've ever done before, but it's almost impossible to do that. Okay, so what we're arguing then is that we need this evolutionary system of systems convergence paradigm, which is a way of like putting everything together. And so there are three key parts to this. We need this system of systems framework, computational framework, a decision support system, and a pedagogy. So I'll explain those in a little bit more detail in this diagram here. So here we're talking about converging Anthropocene systems across regional and urban scales. And so at the top here, we've got the Chesapeake Bay watershed, and we've got Baltimore. So that's like the regional and urban scale. And then we've got, the Columbia River Basin with Portland. So that's the regional and the urban scale and so on. And so then down here at the bottom, we've got our Anthropocene systems that are all co-evolving and interconnected. So we've got geophysical, biophysical, sociocultural, and socio-technical systems. And so we need models of those systems. This is all so complex that we can't, even begin to think about what actions to take if we don't use models. So we need models. And so then the idea is, some of those models could be what we refer to as white box models. So for us engineers or scientists, a white box model is a mechanistic model where we understand how everything kind of works. But of course, we don't have models for all these systems. So we may have to start with machine learning models where we use black box models. But then there's also this kind of intermediate version where it's called theory guided machine learning, where we put some of our mechanistic details in, but maybe we don't know everything. And we sort of use machine learning to fill in the gaps, so to speak. So we can refer to those as gray box models. But however we develop the models, what we want to do is to put them into this the system of systems computational framework shown in the middle here with these kind of green circles. So that's our computational framework where we kind of integrate all this knowledge. And then in addition, we need this pedagogy because we have to train people to implement this entire thing. And we also need a decision support system, which means we've got to interact with stakeholders. So let's say we've got Baltimore is our urban area in the Chesapeake Bay watershed, and Baltimore has some of these problems like disasters and climate change and renewable energy. So then we have to interact with the stakeholders from Baltimore, and they're going to work with us as we try and help them address these societal challenges. So that's how the whole thing sort of fits together. And here we're going from the regional to the urban scale. But you could also imagine something similar going from the urban to the building scale. So now here at the top, we've got the urban environment with all these different systems. And here at the bottom, we've got a single building in this urban environment. And just quickly, what I hope you can see is that some of these systems, like energy, water, air, they're common across these two scales. So you can kind of go from the urban scale to the building scale, and those systems that are common across those two scales should be able to go sort of between those two scales and be kind of coherent. But of course, this is a massively complicated thing, but at least we should think through it and see if we can do it in a better way than we're doing now. Okay, so that's like this evolutionary story. And so now I'm going to focus on these socio-cultural systems. So these are our human systems, and I think you can all agree that we need to understand how human systems work, because in a way, we are the key to addressing these problems. We caused them and we have to address them, and no one else is going to do it for us. Okay, so then, I'm not a social scientist, but the way I understand it, and I have colleagues who've sort of agreed with this, that these are some of the key elements of socio-cultural systems. So we have individual humans in these socio-cultural systems, and we process information using our own cognitive systems. We cooperate and compete with other individuals, and that includes conflict, using these communication systems. We acquire and lose status and leadership positions. because leadership is important in these socio-cultural systems. We acquire and forget knowledge, which is transferred from generation to generation. We also acquire and forget norms and institutions, these kind of socio-cultural, evolutionary features. And also we form alliances with other individuals. So now we've gone from an individual to a group of individuals. Okay, so we're sort of scaling this whole thing up. We've got individuals and groups of individuals. So in the very same way, groups of individuals cooperate and compete with other groups using communication systems. Those groups acquire and lose status. They acquire, of course, there are leaders, but that's in it already. They acquire and forget knowledge, norms, and institutions, and form alliances with other groups. So here we have a sort of a basic scalable structure going from individuals to groups of groups, and overlapping versions of these sort of scalable agent-based structures propagate through all socio-cultural systems. And then the ones I identified previously, these kind of governance, economic, educational, and legal systems, these kind of guide and constrain the evolutionary dynamics, but they're basically sort of comprised of these same sort of structures as all these sociocultural systems have. So then there's another interesting side to this. So, we're all interested in polarization and diversity and equity and inclusion. This is a key challenge right now. So there's this idea known as the paradox of diversity. So I think you can all easily agree that, humanity's greatest achievements and absolute worst atrocities all required cooperation. So this cooperation is something that we are good at as humans. And then the paradox is that diversity empowers innovation with our collective brain, because we've sort of shared knowledge in our collective brain. And then if we have different ideas, in our brains, we sort of share those new ideas, and this gives rise to innovation. But if we have diversity, then even though we may get good ideas from that other brain, that diverse brain, we tend to shy away from those people because, they're from a different socio-cultural group. So this is the paradox. And so then there's this idea of cultural evolvability. So, a socio-cultural system is an evolutionary system. It evolves, and these norms and institutions are the key things that keep those, that evolution going. And so the idea is that we can change some of the institutions, like maybe we can encourage, or sort of reward group effort rather than individual effort. And in this way, we sort of reward cooperation rather than competition. And we don't want to, we don't want to eliminate competition, but we have to have the right balance. So if we sort of change some of these institutions, we can make the system kind of evolve in a better way. And so that's this idea of cultural evolvability. So the idea is we can sort of try and resolve this paradox of diversity by kind of combining the best solutions from different socio-cultural groups and from different disciplinary cultures. And in this way, we can create conditions conducive to larger scales of cooperation and actually also greater levels of innovation. So anyway, this is the idea. And you can read this book by Michael Muthukrishna if you want to understand these ideas better. Okay, so now I've got this kind of middle section on identifying and decomposing Anthropocene systems. So, instead of sort of doing this bottom-up incremental research where we all start with our little piece of this huge, complex system of systems, what we need to do is sort of step back and get a coarse scale overview of this entire knowledge domain. And we sort of, I think it's obvious to anyone that, addressing any kind of problem, that what we need to do is sort of get it roughly right at the beginning and not precisely wrong. So we sort of need to look across all these systems and try and sort of set something up that can eventually take all of them into account. So I feel like a good example of this is this idea of sustainability. And I remember, this is kind of where I started when I started on sustainability, I don't know how many years ago. And, where they were saying, okay, we need to coordinate or integrate environment, economic, and social systems. So this all sounds great. I have a warm, fuzzy feeling when I look at this diagram. But, what exactly am I meant to do here to create a more sustainable world? And so then, quite a long time ago, when I was just starting, I found this kind of a nice figure from this guy Bossel, and he has these same, environment, economic, and social subsystems. But what he's done is like separated them out here into these different sectors. And so I thought, okay, that's what we need to do, because now I can see, where I can get involved here, and how these different sectors relate to each other. But I mean, of course, this was a very useful sort of concept for me. But I feel like now I realize that this, it sort of starts going down the right path, but it doesn't go far enough. And actually, what we have is something like this, which is what I've just described earlier, with this sort of globally connected meta ecosystem, and all these different systems, evolving within this ecosystem. So it's also encouraging that other people, other major institutional players are recognizing this same sort of problem. So there's a relatively new initiative, or like a reimagined initiative, called the One Health approach. And so I'm just taking this figure from the One Health approach. And what you can see in the middle here is what they're trying to do is to have, I don't know where to start here, maybe healthy ecosystems, healthy animals, and healthy humans. And we have to have all of them, all of that balanced, And in order to do that, what we're going to have to do is sort of integrate these different sectors and disciplines shown up here on the left. So we've got the environment and animals and humans. And we're going to have to take into account, the various representations of society within these sectors and disciplines. So we've got, regional and global, local and national, and urban and rural, and so on. So then maybe the most important thing, I think, is what they recognize is that we need to be able to communicate, we need to coordinate, we need to work together to do this. We need to have capacity building to build up the capacity to do this kind of thing. And that should all enable us to collaborate in this massively complicated problem. And you can see this is also from the One Health sort of document. You can see they trying to integrate across all these societal challenges and environmental challenges and animal health challenges. They've got cultural, technological, political, the whole shoot. And so I feel like they understand the nature of the problem. So there's another interesting twist, and here I'm showing you a figure from a paper by Michael Muthukrishna and his colleague. And so this kind of shows you that, you might be tempted to say, oh, okay, we'll just take a model of an economic system, take it off the shelf and plug it into our system of systems. But actually, the current versions of economic systems may not represent, may not be evolutionary. They may not be coherent from an evolutionary perspective. So here, what Michael is showing is that, way back when we had neoclassical economics, we just had economics. And now, well, as we move forward, we combine economics with psychology. So then we had sort of behavioral economics, and then we had economics with psychology and cognitive science. So maybe you can think of this as behavioral science, and we had nudge theory. But in a sense, none of those are sort of sufficient. And where we're heading is to start with those three: economics, psychology, and cognitive science, but then add to them evolutionary biology, anthropology, neuroscience, historical psychology, and dual inheritance theory. So I hope you can sort of see that what's being shown here is more or less a kind of a system of systems, and that what can be achieved if you are able to do this is to address, these problems like shown on the right here, large-scale cooperation, public health, sustainable development, corruption, paradox of diversity, and so on. So then there's one final example I'm going to give you, and that is this kind of the health connection. And so what I've shown you here on the left are those Anthropocene systems I mentioned before. But if we think about humans, then humans a human body is a kind of a system of systems itself. And here we have some of those systems, and they're represented in the middle here. And so then there's kind of connection, between the cognitive and the communication system with our nervous system. And so there's a kind of connection that, that puts humans in the heart of all these Anthropocene systems and kind of leads us to things like systems biology and systems medicine. But more of that in another presentation, let's say. So, okay, so now I've finished the sort of evolutionary side of the story. And what I'm going to cover now is the systems engineering side of the story, which is a kind of a quicker or shorter side of the story. So then what I'm going to start with is how we would sort of put together this system of systems convergence paradigm. How do we bring it to life? So now I have an excellent colleague. His name is Amro Farid, and he came up with this figure. And you can think of this as like a metacognition knowledge generation map. And so we have these 5 domains. And on the left-hand side here, we've got the real world domain. And we would have, real world Anthropocene systems exist in that real world domain. So then what we need to do, if we're trying to develop models of these systems, we need to engage in systems thinking. And we'd need like an abstracted conceptual model of that system. And then we need to translate it into the visual domain and create a visualized conceptual model of that system. And then we translate it into the mathematics domain where we create a mathematical model of that system. And finally, we put it all into some computational environment and crunch the numbers sort of thing. And then we have to be able to circle around this knowledge generation map, because that's kind of how we make progress when we do these things. So now I'm just going to briefly highlight each of these domains. So this is the real world domain. We can do, experiments. We can supplement those with remote sensing. But some of these real world systems are just too big, so we may not be able to do experiments. So that's kind of like the setting we start with. And then this is the systems thinking domain. So this is the primary means of managing cognitive complexity. We think through these systems and identify all the sort of subsystems and all the elements and how they interact with each other. This is basically what we have to do. And you can learn this with good pedagogy. But this kind of systems thinking is subjective, by definition. So the conceptualization, formulation, and interpretation, it's all subjective. And, we can sit around in groups and we can engage in systems thinking until we blue in the face, but we can't actually make decisions because we don't know, we don't have a model of those systems, basically. So then we also have a visual domain. And in a way, this is like the most important domain, because this is where we bring all these different ideas together. But the problem is we all have our own visual domains. So, mechanical engineering, electrical, civil, we all have our own kind of different ways of representing the world visually. And they also, they're discipline specific. So we have to overcome that sort of discipline specific aspect of our sort of ways of representing the world. So then, of course, we've got mathematics. So we have to engage with mathematics to the full extent that we can. And then finally, we're going to, we have to use computational tools to address these problems, because it's only in the computational environment that we can handle the sort of unprecedented scale and heterogeneity of these systems. So that brings us back to our metacognition knowledge generation map. And I hope you kind of see how all these things sort of relate to each other. So then what we're going to do now is I'm going to briefly tell you about this system of systems computational framework. And so that involves this approach called model-based systems engineering, MBSE. And actually the systems engineers, okay, I'm not a systems engineer, but I now know that they've been working on this approach, this model-based systems engineering, for decades. And they've been doing it to address these large, computationally complex problems that they work on. But in general, they only have worked on socio-technical systems and not these Anthropocene systems. So anyway, they use this systems modeling language, SysML, and it's an integral part of systems engineering, and you can use it to represent any ontology you want. So this is a really powerful advantage. There are no limits in scale or heterogeneity. You can like zoom in and zoom out to your heart's content. There is no sort of computational tool attached to it, but I'll show you one that we have attached to it. And then this is kind of what I said before. Traditional systems engineering has been using these tools, but they haven't applied it to Anthropocene systems. So this is a SysML diagram. It's a block definition diagram of what's known as the American Multimodal Energy System. So this is a model that's been developed by this, or has been developed by this colleague Amro Farid. And this itself is a kind of a system of systems. It shows all the various subsystems in the energy system. You can see it's got coal, natural gas, oil. There are other things. There's electric grid. There's energy exports, water treatment. I think there's an economic system here, and domestic supply of coal and oil. And so you can see it's sort of got everything in this one system of systems. And this has all been developed already. It exists. So it's an example of one of these system of systems models. And then this idea of heterofunctional graph theory, it starts with that SysML model. So it uses that SysML model, which shows how everything is connected. And it takes that information and sort of algorithmically puts it across into the mathematical and computing domains. It would take like a whole one semester course to understand the full details of that, but just to kind of give you a sense of how it works. And so this is this heterofunctional graph theory. It's a fusion of model-based systems engineering, which is what I just mentioned, and also network science, which is often used to sort of show how things are connected. But it's like a more sophisticated version of network science. So the idea is anything you can do in network science, you can also do in heterofunctional graph theory, and it's based on model-based systems engineering. And it came from manufacturing and production systems where, the structure and function of all these products changes very quickly, and you need to be able to do that. It's already been applied to many socio-technical systems. So, electric power, water, natural gas, and even healthcare systems. And the operands, so the operands are the things that like move around in these systems. So they include things like matter, mass and energy, which is what we normally have in our models, but then also information, and money is a kind of information. So you can represent economic systems like that. And even though it hasn't really been applied to, ecosystems, we can also represent living organisms of any scale and complexity. So it's a very versatile sort of approach. And so that's this framework. And then finally, I'm just going to quickly tell you about the pedagogy, which is sort of the kinds of things that we need to know in order to be able to implement this whole approach. And maybe I should emphasize now that, it's not like we'll have everyone doing everything. This is just not a viable approach. So different people would have different strengths within this paradigm. So we go back to our metacognition knowledge generation map. And so then we would need skills like experimentation and remote sensing and systems thinking. And we'd need to know the systems modeling language so we could represent all our models visually. We'd need to have experts with applied mathematics skills and also computational science skills. We'd also have, we'd also need people who can like translate from the real world to the systems thinking, to the visual, to the mathematics, and to the computing domain, because that's something you have to do when you're developing these models. And we'd need to have what they call stakeholder engagement or participatory modeling, where we learn how to work with stakeholders and how to bring their problems to life within our computational environment. And we'd have to have visualization skills so we can look at complex results from this computational environment and interpret them in a way that makes sense. And also storytelling skills, because quite often we have to tell stories. I'm sure you all know that narrative and storytelling is sort of the way we convey complex information. And so we need to have people with those skills who can help us, interact with the world and with the stakeholders and with each other and so on. So what I've got to do now, I'm in good shape time-wise, is just to briefly show you this new project that we've got, which is starting to to implement and validate this convergence paradigm. So we're doing it in the Chesapeake Bay watershed, which is shown up here on the right. And so that's the whole region, is this entire watershed. And then Baltimore, which is in the middle here, is the urban area. So we've got this region and this urban area. And this Chesapeake Bay watershed, they have these kind of eutrophication problems where they have nutrients, coming from agriculture that run off and go into this bay. And so then the water quality in the bay is affected. They have very low oxygen in the middle, in the deep water in the middle. So this, has negative consequences. So they've been working on this problem for decades, and they've got these different models that they use to sort of try and represent all these systems, and they are integrating them to try and, use them to understand this complex societal challenge more effectively. So in a way here, we're integrating three societal challenges: eutrophication, agricultural impacts, and economic growth. And then these are the systems we're starting with. So we're not going to start with all systems. We just start with a few. And so then in phase one, we are integrating the land use, the watershed, and the economic system. And then assuming we get approved, because we have to submit a report at the end of phase one. And if they approve, then we'll go through to phase two. So then in phase two, we'll add the estuary system and the governance system. So this is the estuary, that you can see in the map here. So then I won't go into any detail here, but this is just to give you a sense of the land use model. You can see this on the right here. You can see the land use in the Chesapeake Bay watershed according to the different land use types. So there's like a land use model. There's in the middle here, we've got a watershed model that exists. So we're taking that watershed model and putting it into our computational framework. And then we're developing this economic model to represent, economic activity in this whole region. And so the first two exist, and the third one we're adding ourselves. And then in addition, there's this estuary model that we'll add in phase two. That's a three-dimensional model of the estuary. It predicts, chlorophyll and oxygen in the bottom water and all those kinds of things. And then we'll also have this governance model, which is actually being developed in a separate project that we kind of linked with, and we're kind of carrying the results from that project forward into our project. And so we'll add this governance model to the system of systems, in phase two. And so then the idea is so that, we start here with the Chesapeake Bay watershed and Baltimore. And if we can show that this whole thing works, as expected, then what we could do is choose other nodes. So like we could choose, the Portland in the Columbia River Basin and Phoenix in the Colorado River Basin. So we could have these three big nodes, and go for some big, National Science Foundation center or something like that to try and put the whole thing together. Okay, so then all I have to do now is just briefly conclude. So I hope I've convinced you that evolution provides a unique way to identify, decompose, and characterize these Anthropocene systems. And our origin story, which is the big history idea, it reveals how Anthropocene systems co-evolved and became increasingly complex and interconnected. So it's a vital part of this entire thing. And then these sociocultural systems, they can be used to coherently integrate behavioral science when addressing these societal challenges. And in addition, we can maybe even use that knowledge to resolve the paradox of diversity and get away from these, intractable, polarized and, inequitable situations. And then that was the evolution side. So then on the systems engineering side, model-based systems engineering provides a powerful way to converge these Anthropocene systems, to sort of put them together in a coherent way. And this system of systems framework with model-based systems engineering, systems modeling language, and heterofunctional graph theory, it all exists already. But it just needs to be sort of retooled for these Anthropocene systems. But what we really need are these, Anthropocene systems integrators. So we need to train people to help us do this. And maybe that's the thing that's most urgently required. And so, just a note to conclude, I'm sure there is still a role for these small scale projects. Unquestionably, we need to do this bottom-up incremental research. We'll keep doing that within specific disciplines. It'll never go out of fashion, but it won't enable us to address these societal challenges. So I've read an incredible amount of books. This is just a tiny fraction of the total, and of course we've got origin story down here at the bottom left, and thank you very much for your attention. Oh, you mute.
Oh, okay.
Great.
Sorry. John, thank you very much. I read your article, Earth Systems to Anthropocene Systems is really impressive, and it's all about big history. It's really very interesting. And we have some questions here. I will put them on screen if you can answer them. Oh, okay. What do you see as the driving force of evolution to begin with?
That's a good point. For me, I guess maybe I should also preface this that I'm not an expert on everything, but maybe you people in big history, you understand this problem that I don't know everything. But for me, I always thought that evolution started with the origin of life. And that genetic evolution, that's where it all started, and it was just sort of, I guess, cooperation and competition, and actually that is how I see it now. Within life, I sort of see it as this process of cooperation and competition. And actually, I'm changing my tune a little bit here as I'm answering this, because I was going to say I also feel like we have to include geological or geophysical evolution. But within kind of all of life, I think you can imagine cells, individual cells, cooperating and competing in ecosystems as individual cells, and then they form multicellular organisms, and they continue in a way to cooperate and compete within individual organisms. So, and then humans cooperate and compete. So I think you can go from cells to ecosystems, or individual species in ecosystems, to humans, and you can see cooperation and competition through all of those sort of forms of life. And so I think that is in essence the driving force for evolution.
All right, we have a long question here. I'll project in parts. Disciplinary boundaries need to be crossed to enable the integration necessary to address the system of systems. However, given our diverse cultures, values, and political regimes, and so on, a single unified approach seems nearly untenable. The world is not only polarized right now, but dialogue among different countries seems almost impossible. How can we find common ground in this context, especially since individual actions often lack the necessary impact? How do we overcome this challenge, and in what ways does ethics play a role?
Yeah. Oh, well, I feel like it's a great question that goes to the very heart of what we're trying to do. And, to be honest, I feel like I don't know the answer to that. But what I'm suggesting, let's say, or proposing, is a kind of a scientific approach, a scientifically kind of credible and coherent approach. And so maybe if we could get the scientific community to recognize that we can't do this piece by piece, and we have to have a bigger sort of a unified approach, which actually, if you look at that One Health, the One Health study, or the One Health approach that I mentioned earlier, that's exactly what they're calling for, is exactly what you just laid out here. So I feel like this kind of convergence paradigm is kind of for the scientists to help us do what we need to do. But in addition, if we include the socio-cultural systems, then we can start to understand how people behave. And I mean, I think we don't know everything about people, about human behavior, but we can get a better idea about human behavior. And then in addition, keep in mind that a lot of human behavior is sort of non-conscious and is influenced by people around you. So it's not like there's anyone in control of anything, and so what we have then are these sort of evolving socio-cultural systems, and maybe this idea of changing the institutions to make people cooperate is sort of the best way of doing that. And so it's almost like we have to understand scientifically how the world works, and then maybe by doing that we can push things in the right direction. But that's about as far as I can see things going, because I'm limited power. I have zero power, actually. Nothing. So what can I do but try and push things forward from my perspective? But anyway, that's essentially the main problem. Yeah.
Okay. Now we have some questions from our board members. They've sent by email these questions. The first one is, when you speak about human agency, you show a progression that goes from individuals to groups and from groups to groups of groups.
Yeah.
That would be a bottom-up path.
Yeah.
Wouldn't you also consider a top-down path? Because individuals okay.
Yeah, no, perfect. No, absolutely. So it definitely is not a kind of a bottom-up. It's just what I'm trying to show there is that we have individuals and we have groups and we have groups of groups, and they're all influencing each other all the time. So that's the reality. And so then how do we represent that? And so, again, I'm not a social scientist. I've got to be a bit careful what I say, but a good colleague of mine who is an anthropologist, he once told me that, if you think about like human behavior, then, you've got like psychology and social science and anthropology, and they all sort of do everything. So they all have different ways of representing, in a way, the same things. So in a way, this is like chaos, because at least in the engineering, we divide things up. Okay, civil engineering, mechanical, I mean, we never talk to each other, but at least we divide them up. So within the behavioral sciences, it's like a very complicated, thing with different ways of representing things. So if we can come up with models of sociocultural systems that we could sort of all agree on as a kind of a, more or less common framework, then I feel like we could make progress. But without that, I feel like it's very difficult. So anyway, I'm obviously agreeing with you that nothing's bottom up or top down. It's always both. And I'm sort of using your question to say we need better models of these sociocultural systems, because in a way, they're the key. We are the key to addressing these problems.
All right. We have another one. Where it is? Just a second. All right. I lost the question. Just a second. Oh, here it is. Can you give more examples of how the connection between system engineering and heterofunctional graph theory has been applied?
Okay, a good question. I guess this is really where my colleague Amro Farid should answer this, because he really is the expert, and I'm not even competent yet at this theory, but of course I'm telling you about it. So, but then, like I said, systems engineering has used what they call model-based systems engineering for a long time now, and that includes SysML, the systems modeling language, and they apply it to many socio-technical systems. The aerospace engineers, like the defense, aerospace, defense, they all use this in a big way. So model-based systems engineering and SysML have been used a lot. But then heterofunctional graph theory hasn't been used that much. But this colleague of mine, Amro Farid, he has, developed the sort of the overall methodology, and he's applied it to a wide range of different socio-technical systems. And we're currently starting to apply it to hydrologic systems and economic systems. And we think, and we feel confident that it can be applied to, ecological systems and socio-cultural systems. So that's really where it stands.
Okay. Another question. I see in your work a new call for the university's mission. You are integrating mathematics and natural sciences to address pressing societal problems. You are calling for cooperation among many people with different strengths, including the humanities storytellers, with all with systems in systems training for the purpose of solving problems. I guess is a comment rather than a question, or the question might be,
Yeah.
how do you respond to that?
Good question. I like it actually. So, like I love the big picture. I think that's why when I first read, what's an origin story, I was like, I had a sort of a epiphany in a way. I like got the idea, and I thought, okay, I want to do this. But I feel like I feel like humanities must be reintegrated with the rest of knowledge. That's what I feel. That's how I respond. I feel like I see a vital role for the humanities, and in a way, it's not just it's not just history, because we need sort of the humanities to understand how sociocultural systems function in a way, and how they have functioned, and that will determine how they will function in the future, because it's sort of that evolutionary historical trajectory that helps us understand how they behave today in a way. So I guess I'm responding by saying I for sure see the need to include the humanities, and I see the sort of scientific value of narrative and music and dance as being essential to our understanding of these system of systems.
All right. Oh, another one. I'd like to ask you about something I read in your recent article, Earth Systems to Anthropocene. This is the first time I've heard or read autocatalysis used to describe why the rate of evolution has accelerated. In big history, it's often called collective learning. Is this term being commonly used and accepted for this explanation?
Yeah, so this is a good point, actually. And I suppose maybe it would be fair to say that this colleague of mine, who's a second author on that paper, Rupe Karonen from Finland, he liked that autocatalysis term. And actually, all that term means is that sort of things are speeding up. That's all it means, nothing more than that. And I think it's true that things really are speeding up, and they're sort of speeding up in a catalytic way where new technology makes it easier to come up with new technology, and new sources of energy make it easier to come up with new technologies. So things really are speeding up, but it means nothing more than that. But from the point of view of collective learning, I feel like when I read Origin Story, what I didn't really see was the sort of more detailed account of cultural evolution. And I think that cultural evolution is really how sort of social learning works, and that maybe it already has been included in your latest version of big history, but I feel like cultural evolution sort of is the evolutionary description of social learning. Mm-hmm. Of course, there is learning that happens without cultural evolution, but which is also social learning. But cultural evolution wasn't so well represented, but I feel like it could be better represented in big history.
Okay, it's like a reinforcement system.
Yeah.
Another one. Since the details of the future are not predictable, can uncertainty be included?
Yeah. So this is a great point. But so this is what all my engineering colleagues say to me. They've got their model of their watershed, and they've been working on this thing for decades, and that thing's pretty good, or maybe they've got a model of an energy system, or a transportation system. And these things are they're pretty good models. You can predict, to some extent with those things. And then they can evaluate uncertainty, and then they say, but when we include all those other systems, uncertainty will blow up. That's what they say. And so all I can say is, I'm sorry, but if you can go ahead and predict, using your model of a watershed, you can predict your heart's content, and that's a good thing, But if you're trying to solve the world, these societal challenges, then don't think you can do it in the same way as you can for your watershed model. It's just the sort of the order of magnitude of the problem is just like so many times bigger, and so I don't think, we sort of, I'm not sure we will ever be able to get away from that problem. It's sort of just fundamentally unpredictable, the future. But I think what we can do, there would be, I guess what I would say is there would be some systems that are relatively more predictable, and some systems that don't evolve as quickly as other systems that might also be more predictable, if you know what I mean. So that there would be sort of some systems within the system of systems that would be more predictable, and then there'd be others that aren't that predictable. But still, I think it's obvious, if we're going to, try and improve the way the world works, we have to understand it from a kind of a scientific point of view. So somehow getting at the basic knowledge and understanding is the first step. And so that's about as good as we can do in my imagination.
Okay. Oh, I have another question. How can multiple stakeholders value systems be integrated to suggest solution path?
Yeah. So of course so I think what we need, as I showed in one of my slides, we have this computational framework, and then we have a decision support system. And so we need like a special training for people involved in interacting with stakeholders, so we can bring the stakeholders' values to life when we integrate those with our modeling tools. And there may even be times when we need to kind of change the values of the stakeholders. So actually an interesting thing is in this Chesapeake Bay watershed, a colleague of mine recently showed that these stakeholders, they've got a lot of stakeholders in this Chesapeake Bay watershed, and these stakeholders, they, over the past decade or so, they've almost been like trying to game the system to their own advantage, if you know what I mean, because there are big financial stakes. Millions of dollars get paid to the farmers and that to try and improve their sort of agricultural practices. So, these stakeholders try and like game the system. So, we shouldn't think that, a stakeholder is like this pure individual who comes to the problem with, the best intentions. Quite often, that's not the case, And imagine if you're like in a current urban environment in the United States, and you have two political parties and that are like at each other's throats, and, these parties are represented in the stakeholder population. This is not going to be an easy thing to address. So I feel like there too, understanding these sociocultural dynamics and maybe being able to like change the institutions in a way that pushes that stakeholder system in a more cooperative way might help. So the best we can do is sort of try and understand human nature and use our kind of scientifically credible knowledge of that human nature to push things in the right direction. But of course, I'm not setting myself up as the supreme, director or dictator that's going to, be there. You know what I mean? We don't need that, so it's a complex thing.
Of course. Very well. We have 1 hour of seminar. I would like to thank you, John, very much for the presentation. I'd like to thank all IBHA members who sent their messages and questions through email and on the chat box. I think, John, you can answer further questions. You put your email on the description of the video.
People happy to do that. Yeah.
Yeah, of course. So thank you very much, you all. Thank you for watching this presentation. Thank you, John, and thank you, Lowell, for organizing that. I'll call Lowell again. Where is it? Thank you, Lowell. Thank you very much.
Thank you, Lowell and Daniel.
Bye-bye. See you next time. Bye-bye.
Yep.